So I will tell you about developments about black holes that happened before the recent developments that you'll hear in the next 3 talks. So let's see why this doesn't work. So first, a very quick summary. So Carl Schwarzschild found that general relativity, the Einstein theory of gravity, predicts black holes. Einstein himself was confused. He thought that this wasn't the case. So, and then it was shown that they are actually unavoidable given the equations of general relativity. Oppenheimer, the former director here at the IAS, was instrumental in showing that. Now, not only that, but then Hawking showed that black holes are actually not black. So he showed that they emit some radiation, then they can be red or white. It's hard to see the white one. And then he also said that they might imply that quantum mechanics and gravity are not compatible with each other. Now, black holes are first and foremost a great distortion in the flow of time. So let me try to explain that. So this person, Schwarzschild, he found the space-time geometry around the spherical massive body. So he considered a star, and he solved Einstein's equations outside and found the full geometry. This geometry has 4 dimensions of space and time. And this geometry tells us many things, but in particular, it tells us how time flows and how the flow of time changes. So far away, clocks flow at a certain speed. And when you are close to the surface of the star, they flow a little more slowly. Here, due to somehow the Zoom transmission, they don't flow very smoothly, but when you get close, when you take the same star and you make it even smaller, time flows even more slowly, and a person here would feel even a larger weight. So here we're taking the same star with the same mass and making it smaller and smaller. And then eventually, when it gets smaller than a certain radius, which we now call the black hole radius, something very weird happens. So someone sitting there would be feeling an infinite weight, and in addition, time would not flow. So it looks as if time gets to stand still. And this is what troubled Einstein. He said, well, surely you can't have something like that. So a star can never become as small as that. But it was shown that no, the star can be this small, and not only that, but the geometry can continue behind the horizon. So just to explain how that happens, I show you this by producing some diagrams, which we call space-time diagrams. So these are diagrams when we try to represent the geometry of space and time, in this case, 2-dimensional. So we have 1 dimension of space and 1 dimension of time. Each point on this space is an event, something that happens at a particular space and a particular time. And someone sitting at a fixed position would be described by a line. Someone moving with some velocity would be described by a line that is now tilted. So this is moving to the right. So at different times, the position is different. And they cross at a particular time and a particular position. So that's the event when they cross. That's the point where they cross. A light ray, again, follows a straight trajectory, which in this diagram is, let's say, at 45 degrees. We've set the speed of light to 1. And finally, if you have someone who's moving with constant acceleration, you would follow a trajectory of this kind, which will approach a particular light ray. And a person who's following that trajectory would feel a force pushing that person to the left, to that side of the screen. Okay. So the force pushing the person to the bottom of the rocket that is pushing, the rocket is pushing to the right side. So that's all in flat space. Now, the idea is that an observer who's sitting at a fixed position outside the horizon is described by a geometry which is similar to the geometry of flat space, but looked by an accelerated observer. So we have this accelerated observer, and we have the light ray, and that's how the geometry near the horizon feels. And the fact that this person feels an infinite force is because it's getting very close and it's accelerating very, very fast. Okay? But you could also choose not to accelerate, and you could choose to fall freely. And so if you have someone who's falling freely, so they can fall freely as they just move they're just moving and existing in flat space, so they can cross this horizon without any problem. So they don't feel anything special when they cross the horizon. But then as they continue going into that region, they feel bigger and bigger gravitational forces that tear them apart. And eventually they go into a region with infinitely big space-time distortion, which we call the singularity. Singularity just means that we don't know what's going on there. Okay? But what we know is that they will die even before they get to the singularity. Okay? Not good to go there. So you should think of this region behind the horizon as a little bubble of collapsing universe. So inside each black hole, there is a region of the universe that is collapsing, a big crunch inside each black hole. And someone who falls in there dies. Okay, a few words about real black holes. So now we are in a time where it's a golden age for astrophysical observations of black holes. And I could not give a talk about black holes without mentioning at least one of them. So I'm going to mention just one of the recent observations. So this is a field of galaxies. So, well, there are stars and there are some galaxies. And we're going to concentrate on that particular galaxy over there. And this galaxy has a peculiar feature that as I start zooming in, you might start noticing it. Perhaps you notice it now. So there is a big stream of particles and coming out from the center of the galaxy. This is very, very big, much bigger than the size of the galaxy. So there is something very powerful going on in the center of this galaxy. And people have theorized that what goes on in there is that there is a big black hole and matter falls into this black hole and some of the matter sort of splashes out and comes out in this way. And recently there was a very nice picture that was taken with a very powerful radio telescope that managed to resolve the region very close to the black hole. So this is light coming from the matter going around the black hole, and the black hole would roughly be more or less this size here in the middle. And it has a characteristic shape, which is what you would expect as if there was a black hole. The size of this black hole that is in there is the size roughly of the solar system. So it's a very big, supermassive black hole. And there is a rumor that they will take a similar picture of the black hole in the center of our galaxy. So now that was one of the experimental aspects or observational aspects. Now we'll turn back to theoretical aspects and we'll remain there for most of the talk. So we will include now quantum mechanical effects when we consider a black hole. And as we said, black holes are not always black. And that's because black holes emit this radiation that is called Hawking radiation. And they have a temperature that you can compute. It's due to quantum mechanical effects. I think Jeff will mention them a little more. And the temperature of a black hole increases as the size of the black hole decreases. So as you make it smaller, it gets hotter, redder, and as you make it even smaller, it looks white. Unfortunately, it looks like the background in the screen. Now, for temperatures of black holes of various masses are as follows. So if you have a black hole of the mass of the sun, the temperature is very, very tiny, too small for it to be measured. So we cannot measure this effect with these big astrophysical black holes that exist out there. However, you could theoretically imagine a black hole that was smaller, that had the mass of a continent, for example. It would have roughly the size of a bacterium, and it would look, it would have a temperature of the order of the temperature of the sun, and it would look white. Okay, so there you have a white black hole. This effect is so surprising that even the name of the black hole was chosen wrong. Now, this temperature is a little funny for the following reason. So in physics, we are used to thinking about temperature in terms of the microscopic motion of the constituents. So if we have a hot gas or a cold gas, the hot gas is hotter because the molecules are moving faster than the ones in the cold gas. In other words, heat is due to the microscopic motion of the constituents of matter. Now you can wonder, in the case of the black hole, what are these moving constituents? And there are various ideas. We cannot answer this very easily. However, something we can answer easily is how much information do we require to describe this motion? And we can answer this easily because that can be done using the laws of thermodynamics and statistical mechanics. So there is a quantity in statistical mechanics, which is called the amount of information, or sometimes called entropy. If you never heard about it, don't worry about it. So it's something that measures the amount of information that you would need if you were to somehow take a picture of that moving gas. So if you took a picture and you say, how many megabytes do you need to describe that picture? That's this number. And this number is the area of the black hole divided by a very tiny length scale that is a combination of the constants of nature, G Newton, the Newton constant, and the Planck constant, and the speed of light, and so on, which works out to be a very tiny distance, very, very, very small, much, much smaller than any distance we can physically observe. But because this distance is so small, this information or entropy is very, very big. So black holes need a lot of information in order for us to describe them. That we just derive from the laws of thermodynamics. Now, these results have inspired an influential hypothesis, something that we have called the central dogma of quantum black holes. Dogma in the sense of assumption. So it's an assumption, and it's an unproven assumption if you start with the laws of gravity. And that's the idea that black holes, if you look at them from the outside, you can think of them as described as a quantum system with a number of constituents given by the area, number of states given by the area. Or said in a slightly different way, the idea is that if you want to describe a black hole from the outside, the black hole could be simulated by a quantum computer, which has a number of qubits that is given by the area. So the memory of this computer should have a size which is of order the area. Okay? That's the size of the hard drive that your computer would need. It's very, very big, much bigger than the size of any quantum computer that exists, and even any classical computer that exists, and so on. Now, we have some concrete theoretical quantum theories which are supposed to describe these black holes. So some more concrete hypotheses, and Subir will describe one such model that has many aspects in common with charged black holes. So he'll describe a more concrete quantum system. But not everyone was agreed with this point of view. So there were skeptics. And Stephen Hawking was the most famous of those skeptics, that there is a reason why this picture, this idea that I just presented, this central dogma, was actually not correct. And Chef will do his best to explain that position. He will try to explain Hawking's position. So as another British person, perhaps. And